But there is a question from Uriel. Hi, is the antivirus book up to date with AI heuristics?
My book actually talks about the heuristic engine, and it talks a little bit about machine learning. Whenever you say AI, you mean actually for machine learning. So yeah, we touch the topics of machine learning and under the heuristic engine in my book.
Okay, so there are several questions related to what you presented. So can you give an example of DMA attacks?
Oh, DMA attacks are actually advanced attacks that are like for the direct memory access. Those attacks will be prevented by our solution called Sindel. This is the startup that we are developing. Those are very advanced hardware level attacks. And, you know, we'll have Amichai Ifrach, one of our founders of Trainsec.net, that will actually it will actually share will take a new course on hardware hacking. So in 2 weeks from now, or maybe 3 weeks, we'll have a hardware hacking online course on demand recordings of something like 20 or 25 hours. Okay, it's like it will be a very huge hardware hacking course. So there you can learn all about all those attacks and how to analyze them, of course, and how to become a hardware hacker.
Okay, there is another question. When running malware in a VM, best thing is to have it disconnected from all other VMs and the base OS too. Is that right?
Basically, you don't want to connect your virtual machine with the bridged mode, because it actually connects to your actual physical network of your home, house, or your office. So we want to use the best practice is to use VMNet and to route it through another machine like Remnux that actually goes to the internet. So it's like you have one machine, goes through Remnux, and Remnux routes it through to the internet. And then you have the best security. If you don't have the option to do that, use NAT.
Okay. So I think we will continue because there's a lot of questions. We will try to answer them, type the answer. So Uriel, if you can also.
And I also sent the link to my book in the chat.
Yes, that's great. So Pavel, please continue. And guys, if you have any further questions, please write them down in the Q&A. We'll keep up time in the end and answer all your questions.
Okay, so thank you. So I'm going to move over to my bigger screen for more convenience, so you won't see my face, but don't worry, it's not such a big loss. Let's talk about a few slides there in terms of developing malware, and then we'll go into the code demo. So generally, when you develop Windows malware, it's not really different than developing any other Windows low-level code. We're using Windows APIs, and some of them might be documented, some of them might be undocumented. We can use normal tools for software development, such as Visual Studio and the compiler that is provided with Visual Studio, but you can use any C or C++ compiler for this purpose. Obviously, testing is critical, especially if you want to target various types of operating systems, you want things to work out, you have to do proper testing. We can cut some corners in writing the code. So for example, we can allocate memory when we need it, but we don't actually have to free that memory. We don't have to close all handles. That's fine, because usually the malware is short-lived in the time that it's actually running. So you don't really worry too much about every little detail there, because once the process shuts down, the kernel will clean up everything anyway. And of course, debugging is done as when we write malware, we write code which can definitely have bugs. And this is, in fact, very common because the code we're really writing is usually very intricate and sometimes delicate. So it's easy to make mistakes. So normally when we want to write malware, or in fact, any kind of software on Windows from a low-level perspective, we have some APIs provided to us by Microsoft. The most common APIs that many people are familiar with to one extent or another is the Windows API, sometimes referred to as Win32. It's not really a good name. It's an old name, but still being used a lot. So this is the classic C API that was there from the first version of Windows NT. A lot of documented functions there, and you can use that, and these are used a lot, such as the functions used by the dark side ransomware. Some APIs are based around the technology called the Component Object Model, or COM. I'm not going to discuss COM in this little webinar. We'll discuss COM in more detail in the full workshop. And then there are other options. You can use .NET, for example, to write malware. You can do that because .NET is really just a wrapper, for one way of looking at that, is a wrapper around the Windows APIs. However, .NET is easier to unpack and demangle and reverse engineer, so it's usually not being used for real scenarios in most cases, unless you take advantage of certain things you find on a machine, such as a PowerShell engine. And then there's a newer API called the Windows Runtime, which is available from Windows 8 forward. This is not typically used to write malware because it offers very little advantage over the classic Win32 API, and many things there are not really geared towards this kind of low-level stuff. But still, you might find some of these API useful. But of course, in this case, you know that you're going to target Windows 8 and later only. So these are kind of the common APIs to use. So when you think about building some kind of software, some kind of code, we're running some kind of process. And so the process has a memory map, and this is some of the stuff you might find in a process memory map. So first, when the process being created, the kernel maps the executable to the address space of the process. And also it maps NTDLL. NTDLL is a crucial, super important DLL that exists in every user mode process, and it exposes what's known as the native API or system calls, a way to actually go into the kernel to do stuff, because at the end of the day, when you want to do things like open files, allocate memory, things like that, only the kernel can actually do that. But you have to ask the kernel, and NTDLL is the gateway to do that ask. Most of these functions, they are undocumented, and we typically use normal Windows APIs that wrap these functions. But it is also possible to use NTDLL directly, which I'm not going to show in this particular webinar. And there are other such DLLs called subsystem DLLs, where the Windows API is implemented, that are loaded into the process based on need, whether they're loaded automatically because they're part of the import, the dependencies of the process, or they're loaded on demand when we actually forcefully call the load library function to load them. And then since we have at least one thread running our main function, there's a stack for that thread. There's something called default process heap, which is used to allocate dynamic memory for small memory allocations. We can create other heaps if we wanted to. If we have more than one thread, then we have more stacks. A stack is on a per thread basis. And if you want to allocate memory in a more general sense, closer to the operating system, then the virtual alloc function is typically used, and we allocate some memory. And then there are other data structures of interest, such as the process environment block or PEB, and thread environment blocks, and so on. Some of them they're actually partially documented and mostly undocumented, but in fact store some very interesting stuff we can use, as we'll see in the upcoming demonstration. So what happens when we call some kind of Windows API function, or even function from the C runtime, such as fread to read the contents of a file, for example? So this would call a Windows API called read file, which is documented by Microsoft. You can find exactly how to call this function by looking at the documentation. This function is going to call the native API called ntread file as part of the NTDLL system-wide DLL. And then this one is going to make the system call work by placing a number into the X register and using the syscall instruction, the x86 64-bit instruction, which will cause a quantum transition to the kernel. The same thread now gets the powers of the kernel and goes into kernel mode. And here we're going to a function there that's going to call the real ntread file function that has the same prototype, the same parameters as the one in user space, but it's actually the real function implemented by the kernel. And this is going to do whatever needs to be done. It might be needing to call some kind of a kernel driver, such as the NTFS file system driver or something, to do the work. So these kind of transitions happen all the time for anything that the kernel is asked to do, such as allocate memory, read from files, create processes. All that stuff requires kernel intervention. And this is the way these calls are being made. So that's kind of a very, very quick and brief talk about how we approach or some of the aspects of development. So I'm going to now start to create something which is going to be very similar to DarkSide in concept, trying to show you some of its techniques. So this demonstration might be a bit long, so if we're going to be short on time, Lior, just let me know, and I'll try to copy paste more stuff instead of writing them from scratch. So I'm using Visual Studio here. Any version of Visual Studio will do. You can create a new project. I'm going to create a simple console C++ application. The languages typically used for malware development are C or C++. This is probably the most common. Other languages come into the fore, such as Rust, but I'm going to keep it simple, try to use a C only. So let's call that something like DarkSide2, put it in some directory here, and create a new project. So the first thing that we've seen that Uriel demonstrates is that the fact that the import table for that executable was practically empty. There's just one function there. That was the exit process function. And we want to create something similar to that. So how can we do that? So let's try. So first, what I'm going to do here, I'm going to remove everything and just have a simple application that does practically nothing, just returning 0 from my main function here. That's all I'm going to do. So I'm going to build that. So I'm going to build, to compile, and link that. So we get an executable. Let's go to our Explorer to find this executable. So here goes. Here's our executable. And I'm going to drag it into total PE, my PE viewer, but any PE viewer will do. And you'll notice that if I go to the import table there, you can see I have a bunch of imports here. So you can see I have this VC runtime something, and UCRT base something, and kernel32.dll. You can see lots of functions there, which is kind of weird because, as you can see in my code, I've actually done pretty much nothing. I've done nothing here. And I just have returned 0. So what is going on here? Where are all these imports coming from? And so the answer is that when we think about writing code, we typically think of the main function as the first thing that is happening. But this is in fact far from true. What happens here is that the main function is being called by a function from the C runtime. The C runtime is actually at the start of the application, and the C runtime does some stuff, and then it calls our main function. When our main function returns, it does some more stuff, some cleanup stuff, and then our process terminates. So essentially, main is far from being the first thing that is being called. And this is necessary. The C runtime is necessary for several reasons. One of them, for example, if you have a global C++ object that needs to be initialized by calling its constructor, then, of course, someone has to do that. And this is part of what the C runtime is doing. If you don't have that, it's not going to work out. So the first thing we want to do here is to remove this dependency on the C runtime. So I'm going to go to the properties of the project. I'm going to select all platforms and all configurations. So if I want to build an x86 version later, or ARM64 version later, I have all these settings already going for me. I'm going to go to linker here and input, and it says here this option, ignore all default libraries. So I'm going to ignore all them, say, yes, I would like to ignore all these libraries, and press OK. So once I do that, if I build the application now, you can see it doesn't really work. So we have a few things we need to do. The first thing is to close the executable from total PE so it can change. And then we can see we have a bunch of unresolved externals. Apparently, the main function that the C runtime is implementing has a different name called main CRT startup. So I'm going to change that to main CRT startup. Of course, we can also use another linker option to change the name to be main, but let's just make it simple.
Pavel,
yeah.
We cannot see your screen. We can now see the presentation.
You don't see my screen?
You switch to the presentation.
OK, so that's not good. Let me try it again.
OK.
Because I think it was working on a different screen for some reason.
No problem.
Let me just verify.
This is the problem with a lot of screens.
So screen 1, I think. OK. How about now?
Yeah, now it's right.
You can see main CRT startup?
Yes.
OK, so apologies for that. So what we have here is now the change of the main function to main CRT startup. I'm going to build that. So now we still have linker errors here, showing some other functions being unresolved. And this is because we have, there's some other stuff coming from the C runtime, such as various checks, which we need to remove. So I'm going to go to code generation. I'm going to remove some of that stuff, such as security checks. We don't need that. And there's a runtime checks, which we're going to disable. These are coming from the C runtime. Let's see if this is good enough. Let's build that. So now it's built successfully. Let's go back to our total PE here and reload the file. And notice that now we have actually no import table at all. We have nothing, not even exit process. There's just nothing. And in fact, we can go ahead and use that as a basis for our code. However, I'm going to do what DarkSide does. I'm going to have exit process here. So I'm not going to actually run exit process. Don't really need to do that. I'm just going to call the function here. So really not going to actually call that even. So it's under if false, and I'm going to have to add an include here for windows.h. And so I'm not going to call this function, but the fact that it appears will actually force the linker to add an import section for my binary. So if I build this now and I go back to my total PE here, we can see an import section now exists, and there's a single import module, which is kernel 32, and a single import, which is exit process. So we effectively replicated what we have in the DarkSide ransomware. Now, you might be wondering, why do we need the single import there? Is that giving us anything? And so this is just something I can probably guess. There are two reasons that it exists. The first reason is that if you have no import table, that might be a red flag for EDRs. They'll say, wow, I have an executable here with no import table. That's very suspicious. The other thing is that when you have an import for kernel32.dll, which of course is a user mode DLL, it forces that to be loaded into the process, which means that other functions there are going to be available. And that's why I think DarkSide uses this approach. However, just so you know, kernel32 is actually loaded automatically for every user mode process unless it is a native application, which is not really something people typically write. But still, we have now this exit process, and we're back in this state where we have just exit process. So what should we do next? What is our next step? Remember, this is supposed to be ransomware, which means that we need to call certain APIs, such as to open a file, to read a file, and things like that. So let's go ahead and do something like this. Let's have a little function called encrypt file that's going to accept a file name. Let's use a C string here. This is just a const character star, if you're not familiar with Windows development. So we want to open a handle to a file. We want to read the contents. We want to encrypt that in some way and write it back. That's what I want to do here. Something very simple, very straightforward. So let's go ahead and do that by calling the create a file function. I'm going to call create file A here to have the ASCII string that I can provide here. So I'm going to first, I want to read the file. So I'm going to have generic read here. And then no need for any security. Want to open an existing file, some flags we don't care about, and template file we don't care about either. If this fails for some reason, I'm going to do a very simple error handling here just to demonstrate the idea. If it fails, it returns a value called invalid handle value, which is -1. I'm going to just return false here, and I don't really care. Now we want to get the file size. Let's go ahead and get the file size by calling get file size, another Windows API. And we're using those Windows APIs just like normally, but the problem here is that it's going to appear in the import table, which we want to prevent. In fact, we'll do that. There's another thing here, which is about, I think, sharing. So let's do a 0 here. We don't really care about, or maybe just file share read. Of course, don't worry, this code is going to be available after today's webinar, so you can look at that code for as long as you like. Now I'm going to allocate some memory to read the contents of the file. I'm going to do that in this way. It's not the only way to do that, but it's one way that works. I'm going to use the virtual alloc function. I don't care about the address. Here's the size that I need. I need the memory to be committed and reserved. That means it's going to be available immediately. And I want that to be a read-write bunch of memory, so I can read to it and write to it just normally. And once we have that, again, I'm not going to do any error handling here just to save some time. We're going to read the contents of the file. So I'm going to go ahead and go to the handle of the file. Here's the buffer. Here's this number of bytes, which is size. And then I'm going to get back number of bytes were actually read and some parameter we don't care about. So we're going to do that, and we have the contents of the file. So now that we have that, we can close the file. I'm going to close that, and we can reopen that using a write capabilities. So I'm going to go ahead and copy paste a little code here. I'm going to use create file, but this time I want to perform a write operation. There's no need for sharing this file. It's an existing file. It's, of course, can't really fail at this point. I'm just going to simplify the code a little bit. And we want to now encrypt the contents of the file. So the way to do that is to take the buffer and encrypt it. So I'm going to use a simple XOR encryption for this demonstration. So let's call that key. I'm going to just generate some random numbers. Just for fun. Okay, so this should be good enough for our purposes. And then we can go ahead and use a loop, simple loop, that runs until we hit size. We're going to change the buffer here to point to a pointer to a byte, so we have an easier way to access this as an array. So you can do buffer at index I. Let's sort that with the value coming from the key at index I, but since the key is fairly short, we need to roll over when we get to the end of the key, and this is done using a modulo operator. That's going to be modulo of the size of the key. That's a simple way to perform an encryption. And now the last piece of the puzzle here is to really just write things back to the file. So I'm going to write a file here, just the same thing, and close handle and return true, indicating we're done. So this is encrypting the file. Let's test it. Let's see if it actually works. Let's have a little code here. Let's, in fact, let me move the main function to the bottom. Will save me the time to add prototypes. So I'm going to just call this encrypt file, and I have a file here called temp mandel.png. It's just an image. So here's the image. Let's first build that, see if it works. So of course we can't use auto again. Let's see. That's good enough here. So let's see what happens here. Let's look at the file. So here's the existing file. Here goes. You can see there's a Mandelbrot set for those that care, but this is a proper PNG image. So now I'm going to open a command window to make it a bit easier to work with. What we have here, I'm going to go to where my code is. I'm going to run dark side, and it should have encrypted the file. So if I go back to temp and try to open this PNG, you'll notice that this is what I get, some kind of weird error saying that this is not really a PNG file anymore. It's some kind of junk. And as we know with XOR, if we use the same key, we can decrypt it back. So if I run this again, we now should see the image popping up again, normally as before. So we know this code works, and that's nice. But if we go all the way here to the total P, of course, now our import table is not that simple anymore. Now we have all these exit. It's not just exit process. We have all these other APIs we're using, and these are red flags. So someone tries to call create file, virtual, all of these things might be red flags for various EDRs. So we want to remove the use of these functions. So we need to somehow grab the addresses of these functions in a different way. And typical way this is done is by calling the getProc address function. So for example, I can write something like this. Let's say I want to have a function for create file. I can call the getProc address function and provide the handle for kernel 32 module. So I'm going to use get module handle here with kernel 32. And the name of the function I care about, which in this case is create file A. That's the one that I was using. So I'm going to grab that in this way. And if I go ahead and make this a global variable to make it easy to work with, so instead of just getting the pointer as just a generic void pointer, we can use the C++ decal type to make it easier to provide the type of the function without us having to use the function pointers, which is kind of nasty. So I'm going to go here and make it a global variable so it's easier to work with in any function that we need. So for those not familiar with C++, what we have here, this decal type just automatically knows the type of create file A. Instead of me having to copy all that stuff here and create a pointer to that entity, decal type just knows how to do that automatically because the compiler can infer the type based on the header file. So now that we have this pcreate file here, assuming this in fact works as we hope, then we can go to my code here and I can remove create file and change that to pcreate file. That's going to be the pointer itself. So the create file, I don't want to use it anymore. I want to use that dynamically with pcreate file. So if I go ahead and try this, and if I have errors, then of course I need to fix them, such as this little semicolon here. And if I go back to my total PE to reload the file again, you'll notice that now create file is not here anymore. It is not here. I've hidden it. It's not visible anymore because I've attached to it dynamically. But the price of that is that getProc address is here, which is again a red flag because getProc address is used a lot to bind to these kinds of functions automatically. So obviously not good. But at the very least, I can get rid of all the other functions by just using getProc address. So if we need to use read file, I can do the same thing. I can do decal type, read file, and get the address here by calling getProc address. And again, the same idea. I can do exactly the same thing. Let me put the kernel 32 module here as a local variable just for simplicity. Even that is not good enough because it is still visible. So here we'll have a read file. And again, I'm going to grab this and make it a global variable. Like so. And now again, I can go to my code and change any read file calls to pread file, my global variable, which is the function pointer. And again, we can do the same thing. And once we do that, we'll see that, well, total P has apparently I've closed it, I think, by mistake. So let's go and look at that again. And you can see now that now read file is missing from this list. There is no read file here. So in fact, we can get rid of all these functions except getProc address, which is something we want to do to get to the same way that dark side works. But obviously, the question remains, how do we get access to getProc address itself? How can we find it? We can't call getProc address on getProc address, and we need to start somewhere. There's a chicken and egg kind of problem here. So we have to do something. And the way we're going to fix that is by searching for the export getProc address itself within the PE manually. We're going to do that manually. Essentially, we're going to do what getProc address does, basically, not exactly perhaps in the same way, but the same kind of idea. But we're going to do that manually by looking at the PE itself, by looking